Ever wondered if AI is just good at solving problems, or if it can teach us how to solve them? That's the question driving this groundbreaking study on human-AI collaboration. Let's break it down. Imagine working with an AI to tackle a tough coding challenge or a complex math problem. You brainstorm together, and the AI suggests solutions. But here's the twist. The real test isn't just whether the AI gets the right answer. It's whether you walk away understanding how to solve it on your own. That's what researchers call knowledge transfer, the ability of AI to explain its reasoning in a way humans can learn from. The team behind this study, from Princeton, Stanford, and OpenAI, created a framework called KITE to measure this. They recruited 118 participants with varying expertise, from math majors to competitive programmers, and put them through a two-phase experiment. In the first phase, participants teamed up with an AI to ideate solutions, like bouncing ideas off each other. The AI's job here wasn't just to spit out answers, but to explain its thought process. Then came the real test, the second phase. Participants had to solve the same problems alone, without the AI's help. This setup let researchers see if the AI's explanations actually stuck. Here's what they found. While better AI models generally improved collaboration, the results weren't consistent. Some models, like Claude 3.7 Sonnet, outperformed expectations in math tasks, while top-tier models like Gemini 2.5 Pro didn't always translate their raw power into clear explanations. It's like a chess grandmaster who can beat anyone but can't teach you the game. Useful, but not helpful. This matters because if AI can't explain itself, we risk becoming over-reliant on systems we don't understand. Think of it as manager syndrome, where people outsource thinking so much they lose their own skills. In high-stakes fields like medicine or law, that's a big red flag. The study also revealed something surprising. User preferences varied by task. People liked models that adapted to their needs, whether through analogies, step-by-step guidance, or real-world examples. The key takeaway: knowledge transfer isn't automatic. It requires intentional design. The researchers are sharing their data and tools to help build AI that's not just powerful, but pedagogical. A new frontier where machines don't just solve problems, but help us solve them better. Now, let's pivot to the algorithms that make these AI systems tick. Ever wondered how computers solve tricky math problems without brute forcing every possibility? Let's break down some fascinating approaches from recent coding challenges and how smart algorithms can outthink the obvious. Take the problem of finding the largest rectangle in a set of points. Imagine you're given a grid of dots and need to find the biggest rectangle they can form without extra points inside or on the edges. A naive approach would check every 4-point combo, but that's way too slow. Here's the clever twist. A rectangle is defined by two diagonal points. If you have x1, y1, and x2, y2, the other two corners must be x1, y2, and x2, y1. So instead of checking 4 points at once, you scan pairs of diagonals and use a set to quickly check if the other corners exist. It's like having a cheat sheet for the missing pieces. Now consider recurrence relations, equations where each term depends on previous ones. One problem asked, how fast does the sequence UK plus 1 equals 2 UK, 2 UK 2 converge? The answer: exponentially fast. By transforming the equation and analyzing its fixed points, we discovered it zooms toward a limit much quicker than linear or quadratic methods. It's like watching a ball roll down a hill. Once it picks up speed, it's hard to stop. Next, a challenge about array modifications. Make all pairs in an array have the same absolute difference with as few changes as possible. At first, you might think, just count the most common difference. But here's the catch. A less frequent difference might require fewer total changes. It's a balancing act, like choosing between a quick fix that's messy or a slower one that's elegant. The solution: for each pair, map out all possible differences they could achieve with 0, 1, or 2 tweaks, then pick the one with the lowest overall cost. Finally, let's dive into complex numbers and prime numbers. Picture a complex number z equals a plus pi, where a and b are integers. If z equals square root p, the modulus, then p must be a prime congruent to 1 mod 4. This connects number theory and geometry, showing how abstract math can reveal hidden patterns in the universe. From AI collaboration to algorithmic ingenuity, these examples highlight a truth. The future of problem-solving isn't just about raw power. It's about understanding, whether that's an AI explaining its logic or an algorithm revealing the beauty of math. Stay curious, keep exploring, and remember, the best solutions often come from asking the right questions.